incline with an angle of 25 degrees. Find the normal force of the incline on the eraser. Okay, so step one, draw a free body diagram. So I'm going to go ahead and start with our one we always start with, the gravitational force. Yes, there's a gravitational force acting on this eraser. And of course that pulls straight down. Okay, then is there a surface? Yes, therefore there's a normal force. The normal force is perpendicular to the surface. So to go perpendicular to this surface, I'm going to be going up and to the left a little bit. And that will be my normal force. And if there's a surface, then there could be friction. In this case, there is friction. If there was no friction, this would be sliding down. Okay? Even if there was friction, it could be sliding, but the friction is what's holding it in place. So there is a frictional force pointing opposite of the direction this would be sliding. And it's static friction because it is not sliding. And then we check for tension and applied forces, but there's no rope or string and nobody's pushing on this or pulling on it. So therefore, this is all we've got, okay? We want to know what this normal force is, okay? So we're going to try to find that. And so we drew our free body diagram, and now we want to write down our givens. So we know the mass is 7/10 of a kilogram. And that's it, okay? We can use mass to find the gravitational force, though, so we'll go ahead and do this. The gravitational force is going to be the mass times the gravitational field constant. So the gravitational force is going to be 0.7 times 9.81. And so the gravitational force is going to be 6.867 newtons. Okay, now what can we do? We're kind of stuck. We would want to say that it's an equilibrium so that the net force in the x direction equals 0 and the net force in the y direction equals 0, and we can still do that. But when I look at my x and my y's got 1 and then it's got parts of 2, and my x has 2 parts. In order to have only one of our forces need to be broken into components, what we can do is we can rotate the axes, okay? So here's my regular axes. What I'm going to do is rotate them because the normal force and frictional force are at a 90-degree angle. Whoa, I just grabbed the wrong thing. Okay, got that. I'm going to grab one below. That one. I can rotate these and then line up right on top. So that is what I'm going to do. When we have two forces that are at an angle, but they're perpendicular to each other, what we can do is rotate our axes. So now my x-axis is going this way, which isn't the way it normally goes, but that's okay. And my y-axis is going this way. So I'm now calling this side. This is going to be my x-axis. I'm calling this my y-axis. And that allows us to only have one force, the gravitational force, that we're going to get components for. So we're going to want to get the y component. So this is my y-axis now. So the y component would be like this. And I want to get my x component, and the x-axis is going this way. So this would be my x component. Okay, so I've made myself a right triangle here because my y and my x intersect at 90. And I know the hypotenuse, we found that was 6.867 newtons. I want to find these two sides. Well, I need to know an angle. So we're going to do this one time as a group, and then hopefully you can kind of think through it on your own, or just remember things. This angle is 25 degrees. This is going straight down, and this is horizontal. So this angle right here is 90. Okay, this is a, okay. And then we can look at this, bringing this down a little bit. So this is right here. So we've got these two angles need to add up to 90 because they make a 90-degree angle. Okay, so 65 plus how much makes 90? That would be 25. So this angle is 25. The main thing you need to remember, you don't want to go through geometry, is whatever the angle of the incline is, that's also the angle between the gravitational force and the y component. Then we need to label our components because now we can use trigonometry to solve for them. So I'm going to label the y component this time as the perpendicular because it's perpendicular to the direction of motion. And I'm going to label the x component as the parallel because it's parallel to the direction of motion. And then I'm going to use trigonometry to solve. So I've got this side is the opposite, this side's the adjacent. So to find the perpendicular component, I'm going to use the adjacent and the hypotenuse, which is cosine. So the cosine of 25, the angle we know right there, is equal to the adjacent, I'm calling that the perpendicular component, over the hypotenuse 6.867. Multiply both sides by the 6.867, and we get 6.22. Perpendicular component is 6.22 newtons. And then the parallel component, well, this is the opposite side. It's opposite to 25. And I'll use hypotenuse again, so I'll use the trig function sine. The sine of 25 is equal to the opposite, the parallel component, over the hypotenuse 6.867. Multiply both sides by 6.867. We get the parallel component is 2.90 newtons. Okay, so then we're going back up here. Look at our equilibrium equations. The net force in the x direction is 0. I defined this to be the x direction. So that means the left equals the right. So I've got one force now going to the left, the parallel component. And to the right, I've got static friction. So that means that the static friction, the force of static friction is also equal to 2.90. Then in the y direction, the up needs to balance the down. Going up, this is my new y-axis, so going up we have the normal force. And going down, we have the perpendicular component. Well, I know the perpendicular component is 6.22 newtons. So therefore, the normal force is also 6.22 newtons. And we were looking for the normal force. So we now know the normal force. We ended up finding this other stuff which we didn't use in this problem, but we'll use it in other problems. Here is the solution to the problem that we have here.